So, hi, let's continue. So, till now we have seen two types of vectors. Okay, like first of all, normal vectors. These are elements of vector space. Okay, secondly, called dual vectors, or you can call it one forms or covectors. Okay, these are elements of dual vector space. Okay, note the dual vector space is also a vector space. Okay, that follows all the axioms of vector space. So, uh, if V is vector space, V bar is its dual vector space, right? And for this, since this is a vector space, how do we know? You take dual of this vector space, it is isomorphic to this, or say equivalent to this. We can define this as original vector space. Okay, so the dual of this vector space is denoted as this, and you can say this vector space is also dual vector space of this uh, vector space. Okay, so you can call them vice versa as dual vector space. Okay, so that is how. So dual vectors are also vectors, they are just dual to the original vector space. So based on transformation properties, we can further categorize vectors as like vectors, normal vectors living belonging to this vector space. Okay, we call them contravariant. We define them contravariant vectors. Okay, and second, for dual vectors belonging to dual vector space, we can define them as covariant vectors. Okay, and for such vectors, we have components with upper indices. These are components. Okay, and for such vectors, we have components with lower indices. Okay, these are components of the vectors. But why do we place this as upper indices? For why do we define upper indices for contravariant, and why lower indices for covariant? This is not con, this is covariant. It's just a matter of convention. Okay, just a convention. Okay, you see, but why do we define such thing? Why do we give such names to them? Why do we give such names to them as vector as contravariant vectors and dual vectors as covariant vectors? I have taught this in the previous class with an example, but let's do it algebraically. Okay, so we know any vector is a geometrical object. Okay, in special theory of relativity. Okay, why I am calling it here special theory of relativity? Because I am just talking about passive transformations in the special theory of relativity, because it is just a change of reference frames. It is not changing the vectors. Any transformation will not change my vector, but it will change like its components and its basis vectors only. Okay, so the frames will change, but the vector remains invariant under the transformation. Okay, so we know any vector is a geometrical object in SR, means it remains invariant under coordinate transformations or any kind of vector transformation. Unit vector, you transform unit vectors, you scale them, any kind of thing. Okay, so suppose in abstract sense, this is my vector. Okay, and it can be written as, I mean, I'm using the same Einstein summation. Okay, so it can be written as, okay, we need to know why we are placing this kind of thing upper and lower. So I'm not writing it in any summation form. Okay, I'm just writing with a component and its basis vector. Okay, as E. Okay, I will put the indices later on. Okay, in abstract sense, I have this vector. This is, so this is my transformed vector and this is my untransformed vector. So this means there is like, it can be written as this, it can be written as, this is my transformed. So this is the equation, this is the constraint equation for me. And suppose the transformation is, the transformation like E dash is equals to twice of E, original E. Okay, this is my transformation. So what will happen, what will happen, like, sorry, I have just, wait a second, written opposite. So this is dashed. So yeah, this will be this, and this can further be written as twice of this. Now for this to be invariant, means same as, okay, means same as this vector. Okay, the component, the new component, or say the transformed component should be equals to, what it should be equals to, v by 2, such that v bar is equals to v prime is equals to v by 2, and twice of v bar, v cap, is equals to, it remains invariant. Okay, so this is the thing. Since it is a geometric object, okay, a vector is a geometric object, okay, it must remain same, must remain same in all reference frames, in all reference frames. Okay, and you notice that components uh, components of vector v do transform, or say contra vary with its basis vectors, that is this. Okay, so they contravary means they vary opposite, in opposite sense. Okay, so means if the basis is increasing, the components must decrease. Okay, if it is decreasing, the components will increase, so they contravary. Okay, similarly now, okay, so let's, if they are contravarying, okay, let's define the indices like this. Okay, because they are contravarying, let's define the indices of our original basis to be of lower indices. Okay, and they are the components of upper indices. Okay, so this is in Einstein summation. Einstein summation means you do not have to put a different signature of like summation of sigma, the signature sign of sigma here. Okay, you just assume that these dummy indices which are repeated are summed over. Okay, these are summed over. Einstein summation means repeated indices are summed over. Okay, so we just define this, that because they contravary, because they vary oppositely, we define such indices like in the opposite sense. If the you can define in opposite sense also, that you can define like basis vector has upper indices and components has lower indices. But this is our natural convention, that for vectors, normal vectors, we define our basis with a lower indices and its component with an upper indices. This is just a convention. Okay, so wherever you see that two things are contravarying, you just place the indices, relevant indices, at opposite position. Okay, and when you see they are co-varying, means they are varying in a same sense, in a same fashion, then you place the indices at at the same position, same placement. So suppose this this is my component, I vary, and this is my another component. Okay, so they are co-varying, so they both are co-varying. Okay, but if I have this upper notation and this I have lower notation, means they both are contravarying. Okay, so this is means co-varying. Okay, this is contravarying, they are varying oppositely. Okay, we will see Okay, so here we notice that they to remain to make the this geometrical object, that is our vector, to make it invariant, okay, under the transformations, the components and the basis vectors must transform contravariantly, and thus we define this placement of these indices as at opposite positions. Okay, so this is a convention, so we can write it everywhere for. Okay, so these are what this also means. The dummy indices are also summed over. This means this is equals to the, I have summing over the mu indices also. So for a particular direction, okay, this can be written as this. This is mu, okay, and this is mu. So this is also mu, and this is also mu. Okay, okay. There can be two ways. Either you like put your prime over the objects like bases or components, either, or you put your indices over the indices only, prime or over the indices over. I mean, there are two things. Either you put like this and then put the indices, or you put like normal object and put the prime over the indices. There are two different things and two different conventions books follow. For now, I am just putting the prime over the objects only. Don't think it is a prime over indices for now. Okay, so this will be this and this will be this. Here it is mu and it is mu. Okay, so they are contravarying, so I must put the indices in opposite positions. Okay, so now uh, okay, we have studied another condition, that is, in previous classes, that is, okay, let's check, we'll check this also. Okay, so this is the thing, and it should be an identity. Okay, so it should be an identity. I will place the uh, like this, I will place the indices later on. But since this condition must hold, this condition must hold, so you remember this is the basis in dual space. Okay, and this is the basis in original vector space. Okay, this one. Now this condition must remain invariant because they must be orthogonal no matter which reference frame you choose. This condition must remain same in all frames, in all reference frames. Okay, so we can write this as like this. Okay, now you see taking the same transformation. Okay, taking this transformation, let's denote it by t, this transformation. Okay, so applying the same transformation under t, okay, that is this is twice of this one. Okay, so you can place, because we have defined our original basis with a covariant signature, that is a covariant index. Okay, the lower index mu, we will write it here always mu, as mu. Okay, this is my basis in the original vector space. And since this condition must also remain invariant in all reference frames, if I am transforming this means, what does this mean? That will equals to, okay, so for this to be identity again, okay, omega, or say this basis, must transform again contravariantly. What is the spelling? I don't know. Contravariantly, they must transform in a opposite way. Means this should be equals to this by 2. Okay, so if they are contravariantly transforming, so I must place an indices in opposite sense, in opposite way. Okay, so here this means that this will equals to this multiplied by this, and it will remain same. Okay, it will remain same, invariant. Okay, so you see, since these two bases are orthogonal in all, to maintain the orthogonality condition in both, in any reference frame, we must have like the I mean the both the basis vectors must transform contravariantly, means they must transform in opposite sense. Okay, oppositely. So okay, this is fine. Now similar to vectors, okay, this is a abstract vector belonging to vector space. Okay, this is also a vector belonging to, this is a dual vector belonging to a dual space, right? Since it is also a vector, since it is also a vector, or say a geometric object, okay, it must also remain invariant. Okay, it must be same under the any transformations. So this means my transformed dual vector should be equals to my this one, and if I have this and this, sorry, its basis is this. Okay, and this is the transformed one, and this is untransformed. They should remain invariant. Okay, so you see, since my new basis is twice of this basis, this will imply, and of course this implies that my transformed basis in dual space should transform in opposite sense. Okay, so this will further imply that my components of dual space or dual vector must transform as, how must it transform? It must transform like this to maintain the invariance, right? You can check like this is equals to, this is my twice of this, and this is my half. Okay, so it will give me this. So means they are contravarying. They are contravarying, oppositely varying. Okay, they are varying oppositely. So I can place indices. So of course, see here that for this basis we have defined a lower indices. So this will imply that its component, the vector component, should have, sorry, its vector component should have an upper indices. And since it is also contravarying with this basis, dual basis, so it must have an upper indices. Okay, it must also have an upper indices. Okay, now since it has upper indices, this basis has lower indices, original basis, and it must have upper indices. Okay, so what will be, and now we have checked that it should contravary, then this implies that the components should vary, should have lower indices because they are contravarying this basis and the, sorry, not here, here and here, here and here, here and here, right? Okay, so to maintain the invariance under transformations, okay, we see what are contravarying. Contravarying means oppositely varying, and covarying means varying in the same sense. Okay, you see that the components which have lower indices, okay, or say whatever the object is, if it has lower indices, they will covary with each other, with respect to each other. Okay, so in summary, okay, if I have a vector, suppose the object, okay, and the component, and here is the basis vectors, okay, and the object is suppose a vector, okay, that is suppose this vector v, its component is like v, and its basis vector is this. Okay, and we have a dual vector, or okay, dual vector that is not like this. Okay, it will have component this and it has basis this. Okay, now these two do contravary. We have seen they do contravary, they do vary oppositely. These two also do contravary. Okay, these two also do contravary, and these two also contravary. Okay. To maintain the invariance under transformations, under passive transformations, they vary oppositely. Okay, and you can check that these two will co-vary. They will vary in the same fashion. If this is increasing, this must also increase. If this is increasing, this must also increase. Or if they are both increasing, decreasing, if one of them is decreasing, the other must also be decreasing. So these two also will co-vary. Okay, so the things which are contravarying, we place the indices in opposite sense, and which are co-varying, we place the indices in the same place. So if I am let's define this index first. This is my convention. I have defined this. So since this is contravarying, the indices must be upper, and since this is covariant with this one, it should have lower indices, and it is called contravarying, so it must have upper indices. Okay, now you understand this, why we write such vectors as, okay, like this, and we define these as contravariant vector. Okay, and this as covariant covariant vector. Okay, and while defining this, okay, we define these names, okay, uh, observing the transformation of their components with respect to with respect to our original basis of vector space, that is this one, not the dual one. Okay, and original basis is this one. Okay, with respect to this, this is a contravariant vector, so I should not write it like this. Let me write it combinedly. This is contravariant vector, this is covariant vector. Why we are calling this as contravariant vector? Because the components, okay, observe the how components transform on transforming the basis of original vector space. This is the basis of original vector space. While transforming this original vector space, the components of a vector do contravary with respect to this basis. Okay, and the components of covectors, or say dual vectors, do co-vary, means they vary in the same fashion with respect to this basis of vector space, original vector space. Okay, and this is just a convention. Okay, you can say that with respect, if I define my um, suppose if I take my dual vector space and I define this basis with a lower indices, then of course you will say that uh, this vector component will vary covariantly with this. Okay, and this the components of the covariant vector, that is dual vector actually, will vary contravariantly with this basis. So the definition will be changed. Okay, the naming will be changed now, because now this component is contravarying with this basis. We will say this vector, dual vector, as contravariant vector, and this component is varying covariantly with this basis. Okay, so we can define this vector as a covariant vector, but this is not the convention we are following. The only convention we are following in the while giving names to a vector, okay, since these are both vectors, okay, living there in their respective vector spaces, okay, they are both dual to each other. This is just a convention. Okay, so whenever you are saying that this is a contravariant vector and this is a covariant vector, this means it follows some transformation properties, and this covariant vector will co-vary. The components of this covariant vector will co-vary with the basis vector of the original basis. Okay, basis vector of the original vector space. Okay, so I hope it is not giving you producing any confusion here. Okay, we define these kind of names with respect to this basis, original basis only, not this basis. Why there is also another reason, because we have in the previous class we have seen that the basis of the uh, dual space can be like uh, calculated, or yeah, calculated from the basis of the original vector space by the orthogonality condition. Okay, so you just take this as the primary vector space, primary basis. This is my primary basis, and with respect to this I define things. Okay, so that's how we name the vector. We call vectors as contravariant vectors because its components do very contravariantly with respect to the original basis of vector space. Okay, and the components of the dual vectors do vary covariantly, means in the same fashion with respect to original basis only. Okay, so that's how we name them. You just write it down like this only. Okay, so this implies this. What does this teach us? This teaches that this I mean this ambiguity, or whatever you are saying, ambiguity, whatever you want to call it, teaches that they are actually that these vectors, okay, are dual to each other. Okay, you can take any one and define uh, as per your, and define them as contravarying, okay, as per your convenience. Okay, so dual to each other means no vector among them is more fundamental, okay, or nor the basis of their respective basis, okay, is more fundamental than the other. Okay, no vector among them is more fundamental among them. So dual vector is also a vector, vector is also a vector, and no among them is more fundamental. You don't consider that vectors are more fundamental. You can define dual vectors as vectors, and the vectors are just duals of them, those dual vectors. Okay, so it is just like wave particle duality. Wave particle duality in QM means neither particle nature is more fundamental. Okay, now I mean with respect to wave nature. Okay, now wave nature is more fundamental. It is not more fundamental than particle nature. Okay, none of them is superior to the opposite of it, or dual of it. So this is just duality. Okay, in duality, no no particular thing is more fundamental than the opposite of it, or the uh, yeah, dual of it. So this is the duality, means that's why we call them dual vectors. Okay, and that's how we define the covariant vectors and vectors, covariant and contravariant vectors. Okay, you will just remember now. Okay, contravariant vectors have components that contravary with respect to their basis only. Okay, and uh, covariant vectors do have components that co-vary with the same basis of original vector space, not the basis of dual vector space. It is the basis of original vector space. So this is the main thing I wanted to tell you. Now let's proceed to some more fundamental thing in the spatial theory of relativity. Okay, so let's proceed to four displacement vector and see some transformation properties in the spatial theory of relativity. Okay, so we have some coordinate system. Okay, this is ct axis, this is my x-axis. Okay, now consider the x as all xyz components. Okay, now suppose uh, yeah, this is my two other axis, that is s prime frame. Okay, and I have 2 points A and B, and I connect them with a vector, and this is a vector in four-dimensional spacetime. Okay, so this is suppose x1 or say A. Okay, this is del x A, this is del x A B. Okay, this is A point suppose, and a point in the spacetime diagram represents an event. Okay, this is the thing, and by triangle law you can write, by geometry you can write, for triangular law what you will write, that del x, this is a 4 vector, of course, is equals to, sorry, this is plus. Okay, this is the displacement vector 4 vector. Okay, is equals to the displacement, this 4 vector. Okay, so you see the displacement between A and B points can be written by displacement vector of B 4 vector minus displacement vector of A, this is 4 vector. Okay, why I am writing del of xb and del of xa, there is no difference, but you can define your, like, you can define xb vector as x position, the position vector of b minus position vector of origin. Okay, and you can define of this as position vector of a minus position vector of origin. Okay, that's why I am writing this delta. Okay, so this is my displacement four dimensional displacement vector. Okay, four-dimensional spacetime vector. It is, there is no difference between, no big difference between four-dimensional displacement vector and a three-dimensional displacement vector. It's just there is one more component, that is time component, and of course the one more basis vector. So 4 vector, suppose this is my 4 vector. Okay, in a basis I can write this as x mu. Okay, mm, okay, x mu, and let's write this as this mu, assuming in the Einstein summation, Einstein convention. Okay, the dummy indices are repeated, they are summed over. Okay, and for how this runs from mu indices, mu index run from 0 to 4. Okay, mu index, this is my time component, and these are 3 spatial numbers. Okay, so that's how I mean, we can expand this, you can expand this, and to visualize it more clearly, that this is this one is this one, 2 is 3 is this. You can also write it as like t component of x. Okay, now remember, x represents all space-time coordinates here, not just x coordinate, it represents all space-time coordinates here in general. So x0, we will write everything in x only. Okay, so the x0 component is my t component of this displacement vector, and this is t in the t direction, and this is my in the x direction, if I call it x direction, suppose. Okay, I mean, this x is different from this x. Okay, you can mark them like as tilde or what, to differentiate this x with that x. Okay, this is y axis, and this is z axis. Okay, this is how you expand them. So now we have the Lorentz transformations. Lorentz transformations as, what are Lorentz transformations? We know, like, let's take the t component first, t prime. How many of you remember now? You must remember it. It is a very like master equations of special theory of relativity. So t minus v by c squared and x. Okay, you can check whenever you forget something, you just check by dimensional analysis what should be there. Okay, if you forget here c, suppose if you forget the power of c, you just do the dimensional analysis that the dimension of this factor should be of time. Okay, this is x prime, x minus vt, y prime is equals to y for 1D motion in x direction, of course. Okay, now more symmetrically you can write it like this. Okay, I am writing again and again so that you can remember it well. What will happen here, it will be c and x. Okay, minus v by c, you can write it like this. Okay, and this is y prime y, z prime z. Okay, and you can call it as beta. Okay, this is again beta. Okay, and you can write it like this again by defining your components as like this. This is prime coordinate, this is unprimed coordinate. Okay, this is beta, this is x1. Okay, you can write it as tilde to differentiate. Okay, if you want to, from our x, this x notation. Okay, so this is one component again, and I will have now this minus beta x naught plus x1. You can check it. Okay, x naught, where x naught uh, is my CP, x1 is x tilde, and this is 1. Okay, not prime. This is x2 as y coordinate, this is x3 as z coordinate. Okay, so of course you can write it like this is prime and second coordinate is same, third coordinate is same. Okay, and you can make a matrix out of it. X0 prime 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 2 x prime 3. Okay, yeah, now I can just okay, let me write it, then I will introduce the same thing. Okay, so here it will be gamma, here it will be gamma beta minus gamma beta gamma 0 0 0 0 0 1 1. Okay, and this is unchanged coordinates, unprimed coordinates. Okay, you can in matrix, I mean you can define it like x prime matrix, column matrix, and this is my lambda matrix, which is also known as Lorentz transformation matrix. Okay, and this is untransformed matrix. Okay, this is how you write in matrix form. Don't write this as x 4 vector transform to transform from this. Okay, this is a wrong notation. Okay, don't write this, because this implies active transformation. Okay, not passive transformation. We are doing passive transformations, means the vector itself do not change, okay, by any kind of transformation. Okay, vector itself do not change, but this implies that the vector, on applying the Lorentz transformation, okay, the vector has changed to primed vector, but it has not changed. Okay, actually, since it is a geometric object, it will not change, you know, in passive transformations, and these are passive transformations all we are doing. Okay, in passive transformations, x vector is always remains same, or say displacement vector. If I talk about displacement vector, okay, so this will remain same between A and B points, it will remain same. Okay, what else this means? x prime mu. Okay, now let's introduce a new notation. Okay, I am writing the prime over the indices now. Okay, just note that I am writing the prime over the indices, not over the object. Okay, I have changed my notation. Okay, changed my notation. You can find this notation in the scene Carol books also, from x prime mu to x. Okay, so you will write in summation form. This is the basis vector. Okay, so you can write it like this. Okay, the prime is over the index. And this is okay. This I have talked in the previous classes that dummy indices can be replaced with any indices at any moment. Okay, so let's write, for convenience, let's write this as alpha and alpha. Okay, in the unprimed coordinate. Okay, so uh, suppose this is my equation 1. Okay, so equation 1 in component form can be written as, okay, now just to recall your previous class knowledge that of the rules we have defined in the Einstein convention. Okay, that suppose if I have this component, prime component, and this is an unprimed coordinate in V. I have a coordinate V or nu. Okay, nu. Now this is my matrix. So how should the indices be placed over the components of this Lorentz transformation matrix? This is component form. Okay, and this was matrix form. This was matrix form. This are vector. This is a vector. Vector is a geometric object, so it do not transform. Sorry, it do not changes. Okay, it remains an invariant under transformation, but its components will obviously change. Okay, its components will obviously change under the transformation. So if they are okay, recall the rules of Einstein conventions that the indices must be placed at the same place, uh, at the right hand side and the left hand side. Okay, now this free index, there is one free index here, there should also be one free index. Now remaining should be the dummy index. Remaining should be a dummy index. So this is how I write the components. Okay, and I write this equation or these transformations in a component form like this. So in short, these are Lorentz transformations in tensor form or tensor indexes in indices form. Okay, so this is a compact form of Lorentz transformations. In compact form, I should write it compact form. Compact form. Okay, so this is the thing. Now you just see, you can check these are the dummy indices and they are summed over. Means this means I will write this as, this is equivalent to, if I rewrite this, it is running over nu from 0 to 4. Okay, this is free index mu prime, and there is new, and this is equivalent. Okay, you just recall the previous class. Now we will see one another thing. Just wait a second. Yeah, also you can read whenever you write a tensor like this. Okay, this represents your row index, and this represents your column index. Okay, this is similar to you have studied in previous classes when you write matrix, suppose like this, and you write a, I, and j. You read this as column matrix, right? Column indices, and you read this as row indices. But of course, here you will read this as row, okay, and you read this as column while you write any matrix components in the matrix. Okay, so what is this? Suppose I have this 1 comma 2, so you read this as 1 comma 2, 1 2 component. Okay, so where it will be, suppose it is the first row and the second column. Okay, and the second column. Okay, but since the rows are running from 0 to 4, okay, so it will be my second column actually, sorry, second row, and it will be my third column, because the indices are running from 0. Okay, because the indices are running from 0, so the first number, one number, will denote to the second row. So this will be my second row, uh, yeah, second row, and this will be my third column. Okay, suppose this is my thing. Okay, so 1 comma 2 will be at second row. This is my uh, sorry, this is my zeroth row, this is my first row, and this is, yeah, this is my first row. Okay, the second row is my first row. Sorry, I'm just confused. Yeah, this is my row for one indices, and the second will be this one. So this here it will be lie, it will lie. Okay, so you just remember this. You can practice this, don't worry. Okay, let's go. What I have to tell you is that yeah, inverse notation, inverse Lorentz transformation notation. Okay, let's find it. You just swap the position. You just swap the index place. Okay, means if this is my uh, Lorentz transformations, means this is my LT matrix, LT components. Okay, so now this will be my inverse Lorentz transformation components, matrix components. Okay, you just swap the index place. How can we check it? Yes, we can check it. How? Uh, I mean, we can check it with a vague notation. Let's write it like this. Mm, you just write it within another notation. Okay, you just swap it, and because they should be summed over. Okay, so you should have only one index, one repeated index. It should be equals to, since they are opposite, I mean the inverse of each other, it should lead to this one. Okay, you can write it like this also, that actually inverse of this here. You just multiply both sides by its inverse and you will get this kind of result. Okay, this is the inverse, and you see this is a delta, chronicle delta. It is summed over. There are two indices, same dummy indices, so these are summed over mu dash. Okay, this is summed over mu prime. Okay, so it will only be non-zero when mu prime will equals to nu prime. So this will become nu prime delta inverse. Okay, this is nu prime, and so you can just rewrite this as, okay, you just like write this as this. Its inverse is actually equals to, okay, where I have replaced my nu prime with mu prime. Okay, we have checked it that the inverse of this is actually this. You just swap it. Okay, you just swap it. Some people, some books prefer writing the swapped one. Okay, inverse inverse components as like this. I mean this. So inverse of mu prime, it is this. Okay, some people write it like this also. First take the inverse and you just write the components outside, and this seems more valid. Why? Because according to the rules of Einstein, you have the indices outside. Okay, you can take this also, but you can't. I mean, it doesn't seems like good to write this. Okay, because the indices are inside it, and then you are taking inverse. But in this case, the indices are outside, and you can just match. Okay, the indices at LHS and RHS to check your rules of Einstein conventions. Okay, so this seems more valid thing. So people prefer to write inverse like this. Okay, so you can also write this as in this notation as like this is inverse matrix and these are its components. Okay, and this is normal matrix whose components are like this. This will be equals to the Kronecker delta identity. Okay, so this is new. Okay, and also you can check that in the other notation, suppose if I have alpha here and nu prime here, then it should be summed over nu prime, and it has beta here, so this will be written as this. This orthogonality condition follows in S prime frame, okay, moving frame, and this follows in stationary S frame. Okay, so both these conditions do follow in both the frames. So of course it should have an inverse, and this condition will be followed in both the frames. Okay, so this is the thing. Let's move forward to check something else. Okay, okay, this class will be a bit longer because I have to explain something else. We know components transform as like this. We call it a displacement vector. Okay, it is a contravariantly transforming displacement vector, and it has both primed axis and unprimed axis like this, and another AB displacement vector. Okay, you can write it in the displacement form, all of these. Okay, these are components. Okay, not a vector. Vector do not transform. So this is the thing, and we have the upper indices here. So you see, this is a contravariant vector. This is a contravariant component. Okay, contravariant vector. Now let's check how its basis transform. Okay, of course you know that it is a contravariant vector. Okay, and in the same, in its basis itself, okay, it will, they will transform contravaryingly. Contravaryingly means they will transform opposite to this vector. Okay, so let's check if it will transform in opposite sense or not. Let's let's assume let's assume a matrix whose elements are used to relate unit vectors that are, suppose this is my u prime unit vector, and of course you can write it like following your Einstein conventions. This should be here only, and there should be a dummy indices now. Let's take it alpha only. Okay, this is unprimed coordinate system and this is primed coordinate system, and the matrix will relate both of this, and this is reflected in the indices. Okay, now, okay, we know that this do not vary under transformations. This do not vary under. Okay, you remember this is 4 vector. Okay, this is 4 vector and this is a 3 vector. Okay, so I can write like this in primed. Okay, let's write its component and as like this only. Nodal. Okay, I was writing this dial to represent the displacement. Okay, but its component can be written simply as this. Okay, let's write it like this only, and this can be written as this, of course. Don't be confused. Okay, that you have written here alpha alpha and here mu prime mu prime. I have already told you that in Einstein summation convention, dummy indices can be renamed anytime, everywhere, anywhere. Okay, so just wait a second. Now you just write the transformations here as this is lambda mu prime alpha, sorry, mu prime and alpha. Okay, sorry, let me write it neatly. This is alpha, not alpha, sorry, lambda mu prime alpha, and this will be alpha. Okay, and how will this transform as? It will transform as matrix this, matrix component this, mu prime like this, and let's take beta because it should not be same as this. uh, the main indices cannot be repeated more than twice. It is another rule. Okay, you just go back and check. So this can be written as beta and this. Okay, the domain indices are summed over. Let's write it like this one. Okay, so just check this, this. Okay, let's write it like components can be commuted at any time. So I can write it like this. Oh, sorry. Just beta here. Leave the vacant place here and write it like this. Mu prime here, and this is like this. Okay, so this is the thing. Okay, so now for this, since the vectors are same, okay, for this to be a consistent equation, okay, I mean valid equation, okay, this rule must follow that this mu prime, this is beta, okay, this should be equals to beta alpha. This should be inverse of it. This means I am inverse mu prime, this is mu prime beta should be equals to this. Okay, or you can write it oppositely like this, that beta mu prime should be equals to the opposite of inverse of this thing. I mean it should be of same index actually. You just take it here and then you will see that beta and alpha are equal. Then you can write it like this one. So at LHS and RHS, number of free indices should be equal. Okay, so you just see that the transformation property, the transformation matrix for the basis is inverse of the transformation Lorentz transformation matrix. Okay, so what did you notice? This implies that the basis vectors transform in opposite sense. Okay, or say contra variantly, okay, with respect to the displacement vector. Let's say 4 displacement vector components. Okay, so I can write this using this equation, and which one was I had assumed this one. Just wait. let's mark it second, let's mark it third, let's mark it fourth. Okay, so put fourth and third, we get the transformation rule for this one as, yeah, this is primed in the primed, and this is alpha. I can write it as alpha. Okay, alpha is equals to inverse of Lorentz transformation alpha u prime and b. Okay, so they transform in opposite sense. Okay, they transform in opposite sense. So let's finish this class by summarizing things that, okay, so we now have a complete, this is complete we now have a complete set of rules describing how to Lorentz transform, okay, Lorentz transform both a vector, okay, or say a contravariant vector components and unit vectors between, this is between two different inertial frames. Okay, that is, what are the equations? So for displacement vector, this can be written as prime mu, okay, and uh, you better write it with inverse, okay, to make it clear. Okay, so this is mu alpha prime and this is mu. Okay, this is the set when going from S to S prime frame. Okay, and also in opposite sense you can write it like this. This is again delta here. Okay, delta in S frame, you can write it like this as this inverse mu here. Okay, and of course alpha here, and this will be alpha prime and prime frame. Okay, this is when going from S prime to S frame. And so these are my Lorentz transformations of components of a vector and its basis. Okay, when going from S to S prime frame and when going S prime to S frame. S prime is a moving frame, S is a stationary frame. And you see that they have different placement of indices. The displacement vector components has upper indices, and its unit vectors has lower indices. Okay, we call such vectors as such components as covariant with lower indices. These are covariant, and with upper indices they are called contravariant. Okay, such that their inner product, okay, when you will take the inner product of these both vectors, these both objects, you will get an invariance. Just try it, because we have calculated the same above also. It will be same as like this. You can just check. Okay, so whenever you are just writing like this with dummy indices, this is just a scalar or a number. Or a number. Okay, so let's end this class today. Thank you.